Okay, this is lesson 18, day 2. We're going to get through the rest of these problems today. And so, the sum of two digits of a two-digit counting number is 5. When the digits are reversed, the number is 9 greater than the original number. What was the original number? To start this problem, you have to realize that we're talking about the digits of a two-digit number. So let's just talk about what is a two-digit number. We don't know what it is, so let's call it mn. That's a two-digit number. And it says that those digits themselves are equal to 5 when you add them. So m plus n is equal to 5. That's great. So now what we have to do is read the rest of it. So we got our first equation there. And it says that when the digits are reversed, so now we're talking about nm, and I'm going to call that my new number, and so I'm going to call that new, and this is the old number, okay? And what we have is that when I reverse them, that value is 9 greater than the original number. What is the original number? Now the problem is that I have it over here with m plus n equals 5. I have them separated. And if I really wanted to know what does it mean to be 19. So let's sidebar on this. 19. 19 is really 1 times 10 plus 9. I got a 1 in the tens column, and I've got 9 in the ones column. So I have 110 plus a 9. That equals 19. That's the value of 19. Right? So I can use that same idea. I'm going to leave it there and I'll erase it in a second. My old number then is 10m, whatever in that 10's position, it gets multiplied by 10, and I add n. The same thing will work for the new number, but it's 10 times n plus m. Those are the values of my numbers. And so when I'm asking, and I'm going to get rid of this here, is that those values differ by 9. One of them is 9 greater than the original, the new one. The new number, which we're going to call is 10n plus m, is greater than something else. And that something else, and we've been talking about making sure you write this correctly, is 9 more than the original number, which the original number's value is 10m plus n. So I need to know that first. I can add 9 to get my new number. These two equations are the two equations that you will use using elimination or substitution to solve. Obviously, we can do something with that bottom red equation by gathering all my terms to the left or to the right, or at least my variables. So in this case, I have it as m plus n equals 5. So then I'm going to keep it, bring everything to the left side, put it in standard form with m being my first variable, n being my second variable. So I'm going to subtract 10m and subtract 9. Or subtract n, sorry. So 10m and minus n. So when I do this, I have m plus n equals 5, and I have m minus 10m, or a negative 9m, and 10 minus 1 is plus 9n is equal to our value over here, 9. I at least now have them in standard form, and I can solve it. We solve that system very easily by multiplying the top equation by 9. And when I go to distribute, I get 9m plus 9n equals 45, not 49. So the m's cancel. We engineered that to happen. And 9 plus 9 is 18n equals 9 plus 45 is 54. And divide both sides by 18. So n has to equal 3. And if n equals 3, I place that up here. That means m plus 3 equals 5. M equals 2. So we know that the digits are a 3 and a 2. The question is, it wants to know what's the original number, and the original number was mn. So it would be actually 23. That is a proper way to do that problem. Now on to the fun mixture problems. Mixture problems are about mixing different percentages of things together to get a required or wanted percentage out. One of the biggest things that we need to realize is that when you mix two things together, they're averaging together, but they'll average together at different amounts. So I cannot mix a 5% solution and a 10% solution to get something bigger than 10% or smaller than 5%. It'll be somewhere between 5 and 10. And so let's go on here and figure this out. We want to get 1,000 gallons of a mixture that was 56% alcohol. It was necessary to mix a quantity of 20% alcohol with a quantity of 80% alcohol solution. How much of each was required? Now, this is the thing. I got a 20%, I have 80% solutions going to be mixed. Now, if I had equal amounts of this, that'd be 50-50, the percentage would be 50%, because 80 minus the 20 will be 60. 60 divided by 2 is 30. It can go up 30 or down 30, and 20 plus 30 is 50, so a 50% would be a complete average of those two percentages. But here's the thing. I want 56%, which is not down the middle. It's a little bit higher than the average or the middle. That means I'm actually going to use a little bit more of the higher concentration to get it to that point. So that's kind of good to know. So when you think about it, you should have over 500 gallons of the 80% and slightly under 500 gallons for the 20% to make it work. So this is how I work my problem out. I will create a table. The table is going to have 3 columns and 3 rows with an extra row on top for our labels. Now, my first column, the one that I don't have labeled at all here, that has missing a box, is what's going to be mixed and what's created. We know that we have a 20% mixture going in, an 80% mixture, and the last box in this one is always the one that we're trying to create. We are trying to create a 56% solution. Now, what you do now is across the top we have gallons of mixture, how much mixture we have, and then we also have one that's called gallons of alcohol. Now here's the thing. If I had a 20% mixture of alcohol and there's 100 gallons of it, only 20% of that 100 gallons is actually alcohol. The rest of it can be water, it can be all this different stuff that's in there that adds or dilutes the alcohol down. And so if I think about it, 20% of 100 would leave me with 20 actual gallons of alcohol. And that's the part, is the 100% alcohol is what we're going to compare at the end. We're trying to get that to be 100% overall when you add things together. Now, we know one other box. So the outside stuff is all set up. Our percentages going down, our labels are going across. The other option, or the other one that we do know for sure, is that there's 1,000 gallons of the mix that was 56%. So we have 1,000 gallons of this 56% mixture. Now, do we know how much 20% is there? No. Do we know how much 80% is there? No. Do not call this one X and this one Y. I don't want to introduce more variables than I can solve for. And so I am okay with calling the amount for x, or 20% x. But there's a linkage here. If you have a vat or this big cup that holds 1,000 gallons, if you have an X amount for 20%, how much is for the 80%? The fact that you can't put more and you can't put less than 1,000 gallons in it. So if I told you that that 20% was 200 gallons, how many gallons would it be at 80%? It'd be 1,000 minus 200, which is 800. So what it is, I'm not telling you, I'm calling it x. And so what it ends up being is 1,000 minus x. Now, if I added those top two together, I will become 1,000. X plus 1,000 minus x, the x's would cancel, I'm left with 1,000. Here's a cool thing about my table. My table always works is the top two add up to the bottom row. And here's also something very cool. As you move across from left to right, you multiply. You multiply across and you add down. So what does this mean? Now here's the thing. I'm not going to use 20% as 20%. I'm going to change that to a decimal, which means it would be 0.2 times x, or 0.2x. It's 0.8 times 1,000 minus x. And it's 0.56 times 1,000. And just like I said before, you add them down, but the top two will equal the bottom. So that means that 0.2x plus 0.8 times 1,000 minus x is going to equal 0.56 times 1,000. I now have one equation with just an x variable. I'm going to distribute here, multiply that, and I can gather my x's and solve for x. And when you solve for x, you know how many gallons of 20%, and then you can go back and you can solve for 80% by subtracting that from 1,000. I'll pause it, I'm going to do my work, and we'll come back to it. We ended up with 0.2x plus 800, 80% of 1,000, minus 0.8x equals 560. When I gather up my x's, I end up with negative 0.6x equals, subtracting 800 from both sides, don't have room to show that, is a negative 240. And I am going to divide by that negative 0.6. And when you do that, you end up with 400 gallons of 20%. And so therefore, when I subtract that from 1,000, we know we have 600 gallons of 80%. And we've just solved the problem. So mixture problems can be very friendly if you build the table and you understand you're going to add down, but you're going to multiply across. So we're going to try the next problem. The next problem, kind of on the same lines, now we're switching over to liters. How many liters of a 64% glycol solution must be added to 77 liters of a 23% glycol solution to get a 42% glycol solution? I'm going to create the table for you. You try it on your own. So I built the table, got 3 columns, 4 rows with a box missing on top. I got liters of solution, liters of glycol, because that's what we're going to compare to make sure that they're the same. And what's going to go down on the first column? First of all, those are the things I'm putting together. I said how many liters of a 64% glycol solution must be added to. So we know we're talking about a 64% and a 23%. And I want to overall get a 42%. 2% solution. Now this one's slightly different than the last problem, because the last problem told us that we wanted to get an overall total of 1,000. In this case, it's saying how many liters, we don't know, of 64, I'll call that X, that's fine, because it's asking how many, must be added to 77 of the 23. So we know this is 77 liters. And that's all we know. It's asking how much, and then the fact that with 23% is 77. That's all we got, but we can still do the problem. The cool thing about it is that you know you do what going down. Right, you got to go, you add when you go down. So our total, we don't know how much X is, but whatever it is, if I add it to 77, that'll be the total amount that I can fit or have in my glycol solution that is going to be 42%. And you also should remember that you're going to multiply across and change them to decimals. So 0.64 times X, 0.23 times 77, and 0.42 times X plus 77. And again, the first two add up to the last row, and we have an equation. 0.64x plus 0.23 times 77. You will probably want to use your calculator for these. And 0.42 times x plus 77. So you take out your calculator and you find that 0.23 times 77 is equal to, oh my goodness, that's not a nice number at all. Is that a problem? It shouldn't be. 0.42 times x is 0.42x. Plus, I'm guessing 0.42 times 77 is not going to be a nice number either. But again, we have calculators, no problem. I would say keep 2 decimal places. And now, it's just like any other problem, gathering like terms. I'm going to subtract 0.42 from both sides. And subtract 17.71. 17.71. Subtract both of those. So, what we have here is when we do our subtraction gathering like terms, we get 0.22x equals 32.34 minus 17.71 is 1463. Oh, not 36, but 63. And of course, the last step is, and I'm running out of room, is to divide both sides by 0.22. And so the 0.22's cancel. I'm left with x equaling 1463 divided by 0.22 is 66.5 liters of 64% solution. Now, does that make sense is the question. Now, is 42 closer to 23 or to 64? And the answer is it's closer to 22, so therefore you should have slightly more, or 23, so then therefore it's closer, you should have more of that 23%. So we found our answer. For this problem, we want to find the weight, or have the weight of carbon in a container of C3H7Cl was 113 grams. What is the total weight of the compound? And the nice thing we have to know here, and it actually gives us, is that the weight of carbon itself is 12, hydrogen is 1, and chlorine is 35. So what we need here is we need to actually find out what is the weight of one molecule of C3H7Cl. And once you can do that, you can compare that to the actual amount of carbon that's in it, to its total, which then allows us to ramp it up, that if I have 113 grams of carbon, that I can go more than that. So I have 3 carbons, and so carbon, we have 3 times 12 for 36 grams. So we have 36 grams of carbon, and hydrogen, we have 1 times 1, which is 1, not 1, we have 7 of them. So we get 7 grams of carbon. And chlorine, we have 1 of those at 35, which is 35. And if I add all of those up, will equal 78 grams per mole. If you want to bring in all of your chemistry class into this. Now, we got to start setting up a ratio. What we're trying to set up the ratio of is carbon to total. And for this particular molecule, that is 3 times 12, or 36 of the weight of the total 78 is carbon. That percentage is going to be the exact same no matter if I have a whole bunch of it or a little bit of it. The percentage never changes. So that is going to stay the same. So 36 out of 78, which remember is the carbon's weight to the total weight, is going to equal, it says that we have 113 grams of it, to how many would be the whole weight of the compound. So 36 over 78 will be the same as 113 over what? What is a total weight? And we establish that by solving by cross-multiplying. 36 times x is equal to 78 times 113. 36x is going to be equal to 8,814. And it's easily solved for x by dividing both sides by 36. And when I solve for x, I end up with 244.8 grams. And what does that mean? That means that is the weight of the complete amount of total weight of the compound that you would need that if you had 113 grams of carbon. So that was the word problems that we're doing with. I think there was 6 total different types of problems, and as our problems will continue throughout the book, they will get more intense, bigger numbers, more complicated numbers. And so have a great day, and I'll see you tomorrow. Your homework is on page 137, 5, 6, and 7.